Hello friends, in today's lecture we are going to see 5-member heterocycles with one heteroatom. So the three most important heterocycles are furan, pyrrole and thiophene, which contains only one heteroatom. Furan contains oxygen as an heteroatom, pyrrole contains nitrogen as an heteroatom and thiophene contains sulfur as an heteroatom. So general, all heteroatoms are considered to be derived from cyclopentadienyl anion. So structure 1 is for cyclopentadienyl anion. By replacing CH group by NH, you will get pyrrole. By replacing CH group with oxygen, you will get furan. And by replacing CH with sulfur, you will get thiophene. So these three are very important heterocycles, that are pyrrole, furan and thiophene. So these 5-member heterocycles are therefore expected to possess characteristics of conjugated dienes and of acyclic amines, ethers, sulfides accordingly. In addition to their tendency to undergo addition reactions, these heterocycles also have characteristics association with aromaticity, electrophilic substitution reactions, resonance stabilization and aromatic sextet involving the lone pair of electrons. Then we are going to see the structure and stability of 5-member heterocycles with one heteroatom. So 5-member aromatic heterocycles are planar in nature, they are pentagonal and contains sp2 hybridization. So these 3 points are very important, that 5-member aromatic heterocycles are planar pentagonal with hybridized atom. Each carbon atom present in heterocycles contributes 1 electron, while heteroatom contributes 2 electrons to the aromatic. Missing parts, essentially the aromaticity. Now we are going to see the resonance. So resonance structures are the sets of Lewis structures that describes the delocalization of electrons in an polyatomic ion or a molecule. So in many cases a single Lewis structure fails to explain the bonding in a molecule or in a polyatomic ions. Due to that, the bonding is shown by using the resonating structures. Due to the presence of partial charges and fractional bonds in a molecule, these bonds are shown by the resonating structure. This describes the chemical bonding in a molecule. The combination of possible resonance structures are defined as a resonance hybrid, which represents the overall delocalization of electrons within the molecule. Now we are going to see the resonating structures of 5-member heterocycles with one heteroatom. So these are the 5 possible resonating structures of heterocycles containing one heteroatom. So due to the presence of one pair of electrons on the heteroatom, the resonating structures are possible for the heterocycles. So initially, when there is a release or donation of one lone pair, there is a positive charge on heteroatom and negative charge on carbon, which shows that carbon atom is electron rich and heteroatom, due to the release of one lone pair, becomes electron deficient. Similarly, due to the delocalization of this pi electron, it shows different resonating structures. So these are the possible resonating structures for 5-member heterocycle with one heteroatom. Now we are going to see the stabilization energies of 5-member heterocycles. The lone pair associated with the heteroatom is delocalized over the ring carbon. So the stabilization energies for pyrrole is 87.69 kilo. Stabilization energies are 66.81 kilojoule per mole, and for thiophene it is 121.10 kilojoule per mole. Now we are going to see the aromaticity of 5-member heterocycles. The aromaticity in these heterocycles is attributed to the delocalization of pi electron, forming an aromatic sextet in which one electron is attributed by each carbon atom and a pair of electron is attributed by the heteroatom. Now we are going to see the aromaticity order in heterocycles. The aromatic character in this pi excessive heterocycle depends on the availability of lone the heteroatom for cyclic delocalization, which in turn depends on electronegativity. Whenever we are going to think about aromaticity, you must know that the availability of the lone pair of electron is very important, which mainly depend on the electronegativity of the heteroatom. More electronegative heteroatom will have stronger attraction for the lone pair of electrons and will make it less available for cyclic delocalization. The example is oxygen. As oxygen has electronegativity higher than nitrogen and sulfur. That's why, due to their more electronegativity, it has stronger attraction for lone pair of electron and will make less available for cyclic delocalization. This is the reason why furan has lower aromaticity than thiophene and pyrrole. So the aromaticity order in these heterocycles depends on the electronegativity of the heteroatom. That is, oxygen has high electronegativity, then nitrogen, then sulfur. Therefore, the aromaticity follows the order as thiophene, pyrrole, and furan. That is, thiophene has higher aromaticity order than pyrrole, then furan. Then we are going to see the dipole movements. Dipole movements in these heterocycles have also been assumed to be evidence of the charged resonating structures and hence delocalization of n electrons. So the magnitude and direction of the dipole moment depend on the resultant of two structural effects of this direction, that is inductive effect and mesomeric effect. So inductive effect is due to the more electronegative heteroatom on alpha body electrons. Mesomeric effect due to the involving n electrons. Now, reactivity of 5-member heterocycles. 5-member heterocycles with one heteroatom, that is pyrrole, furan and thiophene, are pi excessive and are characterized by their ability to undergo electrophilic substitution reaction on the ring carbon rather than to undergo addition reactions. So all heteroatoms containing one, which are pi and thiophene, contains nitrogen, oxygen and sulfur. These are the very three important heteroatoms. So all heteroatoms are excessive and are characterized by their ability to undergo electrophilic attack on the heteroatom is rare in the neutral heterocycles due to the mesomeric electron release from the heteroatom. The heteroatom bears partial positive charge and hinders the attack of electrophile, while the negatively charged carbons facilitate the attack of electrophiles to occur at ring carbon atoms. So electrophilic attack on ring carbon atom in 5-member heterocycles with one heteroatom. We have seen the resonating structure for 5-member heterocycle with one heteroatom. Okay, at second, third, fourth and fifth position, negative charge are possible. Okay, so there are 4 possible sites on which negative charges are present. Okay, So electrophile bears positive charge. That's why they are tend towards negative charge species that are electrophile. That's why this attack is known as an electrophilic attack. Okay, the species is electron loving species. So the attack is possible at second, third, fourth and fifth position in 5-member heterocycle with one heteroatom. Then the reactivity order in 5-member heterocycles. The reactivity of 5-member heterocycles towards electrophiles depends on the electron availability on the ring carbon atom, or measurably electron released from the heteroatoms and the greater stabilization of transition state. The order of reactivity in 5-member heterocycle is pyrrole has more reactivity than furan, then thiophene and then benzene. So benzene is given as a comparison. The greater reactivity of pyrrole towards electrophiles is attributed to the greater electron releasing ability of trivalent nitrogen, making ring carbon atom electron rich, and to the greater stabilization of transition states involving positive charge on the tetravalent nitrogen atom. The main reason behind the higher reactivity of pyrrole than furan, thiophene and benzene, because of the presence of trivalent nitrogen atom. The heteroatom which is present in pyrrole is nitrogen, and that nitrogen is trivalent, making ring carbon atom electron rich and to the greater stabilization of transition states involving positive charge on the tetravalent nitrogen atom. That's why reactivity order is high in pyrrole. So furan is also reactive towards electrophiles preferentially at position 2, and the reason is the same for pyrrole. Since oxygen is more electronegative than nitrogen and withdraws electrons from the ring carbon atom, the positive charge is less readily accommodated by oxygen atom than by nitrogen atom. Okay, oxygen is more electronegative than nitrogen, but reactivity order of pyrrole is higher than furan. The reason behind it is positive charge is accommodated by oxygen atom than by nitrogen atom. That's why pyrrole, which contains nitrogen as an heteroatom, is more reactive than furan. The transition state with oxygen atom, which is positively charged, resulting from the electrophilic attack of furan, is therefore less stable than pyrrole. Thus furan is less reactive towards electrophiles than pyrrole, as phenol is less reactive than aniline. Thank you.